ready for bag. Okay, so just to repeat, you learned about the Einstein A, the Einstein B's. A was spontaneous decay, B for stimulated emission, B for absorption. These require an incoming photons. This is automatic spontaneous decay. And you learned that the A coefficient of Einstein was a result of what are called overlap integrals. Am I getting a projection? Overlap integrals, which was the integrals of the wave functions of upper state and lower state integrated over all space. And sometimes those integrals are zero, and sometimes they are not zero. Okay, great. Where we left off. There's a lot of details in all this physics, as you can see. What I want to do is get to the page that had the Einstein A's defined.
39.
Thank you. Getting there. Here they are. Okay. So the A, the B's, and the B's. Okay, these quantities are the probabilities in units per second time. Okay. And then we found out that this was some overlap integrals, and then we talked about something called the oscillator strength, where we showed that A was equal to some constants times the oscillator strength. Okay, and it's the oscillator strength that we will talk about because it naturally goes into the opacities and absorption coefficients that we'll be talking about. And so the point is that A was the overlap integral of these wave functions. And then we said basically that if you had an electron in state, higher state here, higher state NLM, and okay, this spontaneous decay, this was a wave function of the upper state, and that decayed with an E-folding time of 1/2 of, or the inverse of 1/2 of the A coefficient. So we found out that the E-folding time of this state was proportional to 2 over the Einstein A for that state. Everybody with me? Okay. And it's these relative times, because we're going to find out that the line intensities are related to the magnitudes of these things, but they have different strengths. And so I'm going to fast forward again to this, we talked about this functional formula oscillator strengths, that you can get them in terms of basically N and whatnot, and that you came up with relative strengths for the lines, and you ended up with a hydrogen spectrum. Well, you ended up with an energy diagram that looked like this, where Lyman-Alpha was 2 transitions, Lyman-Beta was 2 transitions, and H-alpha is 7 different transitions with different wavelengths, each one having its own Einstein A, therefore its own oscillator strength. Okay, these being those that obey the selection rules, the dipole selection rules, and that A to B, A always has twice the oscillator strength of B when you have a P to an S transition. Okay, and when you have an S to a P transition, they're 1 to 1, and then this is a P to an S, so it's 2 to 1 for the higher energy to the lower energy. And then you have the IJK, and their relationship was 9 to 1 to 5. Okay, 9 to 1, 5. And so this is the strongest transition, basically because the multiplicity of states are highest here and highest here. And then this is the next one because the multiplicity of states is higher here and higher. And then this is the lowest multiplicity of states, so the probability is lower, oscillator strength is lower. Okay. So really, the relative oscillator strengths come from these multiplicity of possible states that the electron can transition to. And then we came up with the spectrum of Lyman-Alpha, Lyman-Beta, and H-alpha. Okay. Now, I do want to remind you, I checked it. These are backwards on your notes. This is A, this is B. I apologize for that. Okay. A is twice as strong than B, and then when you take the sum of these, the 1/2 to the 3/2 to 1/2 and the 1/2 to 1/2 transitions, and you get what's called the average transition, you get the one that we use in atomic physics, which has a B parameter, a oscillator strength around 0.4. All right, today, that's the, in a sense, how we get the amplitudes of these lines. The energies of each of these lines come from the physics that went into the model. Okay, spin-orbit coupling, relativistic energies, radiative corrections. That's where the wavelengths came from, because the energy states are set by that. Bless you. The amplitudes come from basically the strength of the dipole moment between the initial and the final wave functions. They have a charge distribution in space for the upper state, charge distribution in space for the lower state. The strength of the dipole moment of that charge distribution gives you the relative strength and amplitude of the different transitions. Okay. But since there's also a multiplicity of states, that factors in as well. Okay. You can see that H-alpha, right, the old line that we say is at 65, 63, at least in the air, is in the vacuum more around 65, 64. Wow, what are those numbers? 54. Did I put in the wrong numbers?
That number is just moving towards us very, very quickly.
I think I was supposed to write a 6 instead of a 5. Don't ever try to write a book, people. It will kill you. It will be the death of you. You make so many mistakes no matter how hard you try. Okay, we're done. But anyway, you can see that it is 7 different transitions, all of having different relative strengths, okay? And then here's the average one with an oscillator strength of around almost 0.7. So that's the amplitude. So now I want to just briefly tell you about the amplitude of the ionization edge cross section. Okay. And I'm just going to show you something because when we go to talk about it later, I just want you to know, oh, this is where it came from. And then today I want to talk to you about the shape of the absorption lines. Do something called natural broadening. Okay? That's what today's lecture is going to be. All right. Now, for a bound-free transition, we talked about these K states of the hyperbolic orbit in the continuum around an atom. That its electron started in state N, went up some free state K, okay, and that the energy of the photon was related through this equation for state K, and then it turned out that the kinetic energy, 1/2 mv squared, was the Rydberg constant divided by v squared. Well, again, you can take the wave functions and integrate them over all space, and when you do that, you get this nasty, nasty, nasty expression. Okay? So You got 2s and 3s, you got the multiplicity of states, you got k's, you got n's, you got arctangents of n over k that are in exponents. You got 1 minus n squared, 1 over k squared, minus 7. I mean, it's a mess. But you can figure out now what the oscillator strength is for, Balmer line starting at n equals 2, going to say right to the edge, k equals infinity, 0 kinetic energy. Okay. You can calculate that. But you have to know this function. Well, it was worked out in 1936 or so that this function is these hypergeometric functions, which I'm not going to go into, that are functions of these arguments, and that then you could also approximate them when you carry out these functions. Turns out you can write them, worked out in 1935, as a series of polynomials. Okay? So those polynomials look like this, just to show you. If you're ionizing from the ground state, where n equals 1, up to some free state k, this is what that polynomial looks like. And then here's the coefficient, here's the polynomial for Balmer's, and then for Paschen ionizations. I'm just showing you the formalisms exist. That's what I'm trying to do. And it's complicated. Okay. And this is just hydrogen. Now, if you want to solve for what k is in terms of the energy of the photon, you can do that very simply, because you know that that 1/2 mv squared equals Rydberg constant over k squared. So you can do the conservation of energy, and you can come up with the photon energy is that the value of k, and here's the photon energy, here's the level n from which it was ionized, and you can stick that in there. Just letting you know you can get that k value from the photon energy. So later on, I'm going to talk to you about the shape. Right now, we're just talking about the amplitudes. Well, H nu gives you the shape, actually. But later on, I'm going to show you what the actual forms are for. Remember those cross sections I showed you? The very narrow Lyman-Alpha line one? And then I showed you the ionization edge cross section. So these are where they come from. I'm just trying to teach you where they come from. All right, so today's lesson is going to be natural broadening. And this is about one of the most important things about understanding absorption that there is how a line gets broadened. And we've talked about how it gets broadened in many ways. There's a natural broadening from the atomic physics, which is what we're going to talk about today. And then there's thermal broadening due to the temperature of the gas, and some are moving toward you. And you've probably heard of damped lines. We've talked about them, the lines that go like this. They have the huge damping wings. Today we're going to talk about basically where those damping wings come from. They actually come from the physics we're going to talk about today. Okay? What I'm trying to do is give you a deeper understanding of the spectra you're looking at than you would get in a glossing over. This is a damped Lyman-Alpha line. This is the damped wing. You know, what we were taught is in the center it's a Gaussian, and the outside it goes as 1 over nu squared. Done. Where'd it come from? What are the physics? I have no intuition for it. I didn't understand it at all until 10 years after I was out of grad school. So again, I'm trying to show you things that I hope will fit into your toolbox in the way that I wished they had fit into my toolbox when I was a postdoc and starting out doing, really getting serious about doing research. Maybe a failed experiment, but I'm going to try it this way. Okay. Now, you've all heard of Heisenberg's uncertainty principle. We've borrowed it already. Delta E times delta T is basically on the order of h bar. Okay? Well, we already said that the time, E folding time, that an electron would spin in an upper state is delta t equals 2 over, this is actually an equal sign, 2 over the Einstein coefficient. So we can write this now in terms of the Einstein coefficient. Okay, so what do we get for delta E? Help me if my math is wrong. Something like that, right? Is that what I wrote? Mm-hmm. Yay, I can do algebra. Okay. All right. So now we see another very, very important part of Einstein's coefficient, another very, very important thing that came out of overlap integrals. Pardon me, I have not eaten at all today. Against my own rules, I know. That the energy of this state is not exact. You've probably heard this before. You've probably seen this before. So, when you account for the fact that delta E, this a blurry energy here, means that the photon energy is not going to just be one energy. So if there's a spread in this energy, there'll be a spread in the photon frequencies or wavelengths that come out. Okay? And we know that delta E is equal to H delta nu, or HC over lambda squared delta lambda. Okay? So it turns out that that's about 10 to the 8 hertz for a typical A value. A typical A value is around 10 to the 8 inverse seconds. Okay? So, given that, we get basically a delta nu of about 10 to the 8 hertz. That corresponds, in the optical, to a fractional difference of about 10 to the minus 7 in frequency. So if it's coming out in the optical, which I believe is around 10 to the 15 hertz, and the uncertainty in the energy level is 10 to the minus 7, 10 to the 8 hertz, then it's roughly a fractional difference of 10 to the minus 7 hertz. And you're like, that's so small, why are we even bothering with it? We're going to find out because there's wings. Okay. With lambda, it's about 10 to the minus 4 angstroms because the optical wavelengths is, say, 5,000 angstroms, okay? And we get about a 10 to the minus 4 angstrom spread when we do this calculation here. And so fractionally, it also comes out to a delta lambda over lambda of about 10 to the minus 7. You can't measure that. Why do we care about it? Again, I will say, because the wings of this behavior. Now, this delta t is the E-folding time. This delta E is kind of what you would call the sort of uncertainty width of some energy uncertainty distribution. And the question is, what is that uncertainty energy distribution? Because that affects what the shape of the cross-section is and what the probability is for photons that are just off center of the transition to actually be absorbed. You see what I'm saying? Okay? There's a photon. If this is perfect delta E, and we say for wavelengths of 1215.6701 exactly, come in and the electron goes up. Boom. But no, there's a little bit of an energy spread in both these states, okay? And so if I'm something like 1215.670102, I can still make this transition go up because I don't have to have the exact only single one allowed energy. And what we're saying is that there's a distribution of that, so that the probability is highest for the transition when the photon has exactly the mode differences of the modes of those distributions. But a photon that could come in with this energy, I should say, an energy from there to there could also cause a transition, or an energy that goes from there to there. Any energy difference that falls in these shaded regions, for example, could cause a transition. But this energy difference right here is the highest probable one, and therefore the amplitude's the highest. So you see, everybody get what I'm getting at there? Okay. All right. Now, I want you to memorize that. 10 to the minus 4, 1 part in 10,000ths is the natural width of one of these energy. Okay? I think every professional spectroscopist should know that. 10 to the minus 4. All right. So here is where the mathematics comes in. I guarantee that, well, most books don't treat it this way. I have decided to treat it in which I think is the actual physical way. Most books derive this cross-section shape by assuming something called a classic oscillator, where they have an electron in a forced field and it self-damps itself, and then you solve some oscillator equation and you get out some function which actually isn't the right shape, but if you make some approximations you get out the right shape. And to me, let's do it like adults, okay? Let's do it real. Now, what have we talked about? There's a time-dependent probability of overlap of the upper state and the lower state, okay? We're not going to worry about the M states. We're just going to make life easy now and do NL and N prime L prime, okay? And I'm only going to do the Schrodinger model, okay? So let's pick that one. This is NL, and this is N prime L prime, okay? Multiplication, the square, overall volume of the complex conjugate of this wave function multiplied by this wave function. Okay. Now, it turns out then that this wave function can be written as the spatial part, which we all know is the radial part and the harmonic functions, times the time part. Okay. Now, this is the normal steady state oscillation. Remember, this is an oscillation of a wave, telling you that the amplitude of the wave function is oscillating at some angular frequency given by E over H bar. Okay? The I is what makes it oscillatory. But now this state is going to decay, and it's going to decay with some E folding time, okay, which is 2 over that gamma. And this is the hard part. Got to bear with me. I'm going to write that as a gamma right now. Remember I told you that it was 2 over A for a single state for the E folding time. Okay. But now if you'll allow me, I'm going to write it as a gamma and the reason will become clear. Okay. So N decays at some oscillatory wave function here, which can decay to some other states, okay, at some E folding time, 2 over gamma NL. And the same thing with this state, it can decay. It's an oscillatory function, basically the spatial wave function, which is oscillating, and then that oscillation is damped and can decay at some E folding time, 2 over gamma N prime L prime. Okay, so they're transitory in time. So this is what you have to account for. All right. Here is a complex, or I say, here are the first 5 levels of a hydrogenic atom. S, P, D, F, G for the basically L equals 0, 1, 2, 3, 4, and 5 states, and the N states 1, 2, 3, 4, and 5. And what I'm going to do is I'm going to set up a grid, and I'm going to call this the L state. I'm going to define on the grid of I equals 0 to I equals 4. In the end grid, I'm going to define that as a variable m from 1 to 5. So I'm basically just setting up a grid of L's and N's, okay? Because what you have to do is, let's consider this channel here. This is a decay channel that goes from 5p to 4s. But the width of this state depends upon all possible decay channels, not just the one that we care about. The width of this state doesn't just depend upon the A from here to here. It depends upon all the possible decay channels that it can go, because the more channels that this has to decay, the shorter is its e-folding time to decay, the broader is its energy width. Everybody got that? Now this one has 1, 2, 3, 4, 5, 6 possible channels of decay. So I have to account for all of those channels in order to figure out what its energy width is. That's why I wrote it as a gamma instead of an A. Now the lower state also has an energy uncertainty associated with it too, right? And it only has 2 decay channels. So to get the width of that energy, I have to account for all these decay channels. To get the width of this energy, I have to account for just those 2 channels. And then eventually I have to account for the widths of both of them to figure out what is the distribution of photons that can cause absorption for a 5p to a 4s, or vice versa. Now, are there any questions there? Because that's a key aspect of the cross-section. Okay. So basically, if you go back to the time-dependent part of that wave equation that I wrote down, right here, okay? Because we want to eventually bring it back into this, that time-dependent. It turns out that, you know how e to the x plus y is actually, how does it go? E to the x times y is equal to e to the x times e to the y. Remember that? I think that's how it works. You have e to the xy, that's also equal to e to the x times e to the y. So that's what we've done here.
No.
That's
E to the xy is equal to e to the x to the y. E to the x times e to the y would be equal to e to the x plus y.
Plus y. That's what I thought. Okay. So these are the products. Okay. I think that's where this comes from. Sorry, that's where this comes from. Okay. So what you got to do is you want the total probability for the decay channels for this one. To get the full e-folding time, you take the product of all the A's there. And to get the e-folding, you take the product of those. So to get the total for the state in L, you sum from over m up to n minus 1, because n is the absorption state, and you have to sum over the L minus 1 states, and then you summing also from NL to minus 1, and you have to sum over the L plus 1 states. So basically what you're saying is I'm summing this one, this one, this one, and this one for the L minus 1 states, and then I'm summing, oh, they start here, this one and this one on the L plus 1 states. Okay, I'm taking the product of all those probabilities to get out the final probability, because probabilities are products. But so that's what this is, product of the probabilities. These are the A coefficients for each of those individual transitions. Okay. The A for this one, the A for this one, the A for that one, etc. And then I take the product of those exponential decays, and I get this term. And then I do that for the L plus 1s. But because of this property here, you can take out the fact that this sum here can be made the product of these things. And so basically you find out that the E-folding time of the upper state is the sum of all the A's on L minus 1 plus all the sum of the A's on L plus 1. So in a sense, you're multiplying the probabilities of each of these, but in the end, what does that mean? To get the E-folding time of a photon, of an electron here, to decay to any state at all, is the sum of the A for this, the sum of the A for this transition, the sum of the A for that transition, the sum of the A transition, plus the sum of the A to that transition, plus the sum of the A to that transition. It's the sum of all the A's. That gives you the gamma, which is the E-folding time. And then it's the gamma, which gives you the E-folding time, and therefore the energy width of that upper state. And then you do the same thing for the lower state, summing those two. So basically you have a gamma NL and you have a gamma NL prime. This is the E-folding time for anything to fall from state NL to all possible states. This is the E-folding time for an electron to fall spontaneously from this state to all allowed states. Okay. Finally, because the probability is the product of all these functions, the final width of the distribution of photons that can contribute is the sum of the two widths. In other words, there is some energy distribution here, and there's some energy distribution here, and it's a convolution of those two, and so it ends up being the sum, because when you convolve two, if you convolve two Gaussians, right, one Gaussian has sigma 1 and the other Gaussian has sigma 2, you get a new Gaussian when you convolve them, which is broader sigma, where that sigma is given by this when you convolve these two. Well, with Lorentzians, it's very similar. This is the square root of the width of a Lorentzian, which is the function we're going to find out this is instead of a Gaussian. And so you basically have the sum again. The same principle as this. Okay? Because you're convolving this width of gamma squared and this width, or I'm sorry, of square root gamma and that width square root gamma. Okay? Has anybody seen that before? I didn't think so. So, again, I'm not going to have you derive this stuff on a test. Okay? I'm going to show you the end result. I want you to understand the end result. What I'm trying to do is enrich you so that when you walk away from here, you'll vaguely remember something about what an Einstein A coefficient is, how it came about, how you use it, and then when we talk about something called a damping constant, where it comes from. And in fact, I could have you look up on NIST, National Institute Standards of Technology, tell you to look up some transitions and have you calculate the damping constant from the A coefficients if I wanted to. Just so that you know how to do it if you need to. Okay. All right, part 2. How do we get the shape of the function? And today we're going to derive the Lorentzian. Okay. The Lorentzian, so now we know that the probability distribution is the product of the two wave functions. Going back to this. It's the product of the two wave functions, which are given by this, and then when we make this product, we're going to have e of this minus e of that, and we're going to have these sum together because of the way that those products add. And we end up with this function here. The spatial product of state NL and NL prime L, N prime L prime. The energy difference here, En and En prime, okay? Oscillatory of that, and then the decay, which is given by the E folding time 2 over gamma, which is given by gamma NL, this width, plus gamma NL prime, L prime, this width, and we write that as gamma NL N prime L prime. See the superscript, upper script there. So now this is the true width of the breadth of energies in these photons that can make this transition. So how do we get that shape of that function? Well, okay, this is the time dependent of this equation. Drop out that, the time dependent part of this equation is this. T and T, okay? Now if you take the Fourier transform of that, you get the frequency distribution. This is the energy distribution with time. If you take the Fourier transform, you get the frequency distribution, okay? If you square the frequency distribution, assuming that it's a complex function with its conjugate, you get what's called the broadening function, the line broadening function. We're going to call it phi for transitions from NL to N prime L prime. And it's going to be the product of the Fourier transform of the time-dependent part of the product, probability. The definition of the line broadening function is that when you integrate that shape, whatever it may be, the area under it is unity. That's how it will be normalized. So we take the Fourier transform of f of t, which is this, if you just do your old Fourier transforms. Okay. Carrying out the math, it looks like this. Okay, I've replaced the e's with n's. Here's your gammas. Okay. When you take the Fourier transform, you get this equation right here. Anybody taken electronics? Like when you were in physics, did you take a class on electronics?
Yeah.
And you had complex phase and Q factors in your RC circuits, LRC circuits? Same exact math. Same exact math. Okay. We have an I here. This is the frequency, and this is the transition frequency. And this is the gamma that comes from Einstein A's. Now we take this times its complex conjugate to get phi, and we get c squared times this, and we have this frequency difference here squared, and we have the gamma over 2 squared. So this is the inverse of the E folding time squared, and this is the frequency dependence relative to the central frequency, and that gives you the line broadening function. Okay? There it is, folks. All we have left to do is normalized. We're going to normalize it according to equation 2.8. Now, if you look at the shape of that function, it's known as a Lorentzian. Here's the shape of a Lorentzian. Notice the 1 over pi y x minus x naught plus y squared. Let's go back to this equation. 1 over pi y x minus x naught y squared. That tells you what your normalization is going to have to be. This is what it looks like. Here's the full width, full width at half height. The amplitude is pi over y. And here's what it looks like. Here's the relative x-axis relative to the center location. So delta x equals 2y. Put you out here at the full width, half width. Okay. So anyway, when you do the normalization now, according to the known behavior of a Lorentzian, you get out, voila, the line broadening function. So I guarantee you, if you, well, I always say that, I guarantee you, I don't guarantee, but any other book you go look at, it's going to give you some nonsense about classic oscillators. This is the real McCoy. Okay. What did I want you to learn here? I wanted you to learn that there's a way to get the amplitude of this cross-section that's going to come, and there's a way to get the shape. This is the shape. It's normalized so its area equals unity. That shape depends upon the e-folding time of this decay, which depends upon all the possible channels in that this upper state can fall, and all the possible channels that the lower state can fall. That defines these two widths. You then convolve them together to get gamma, which is called the damping constant. You then take the Fourier transform to get the power spectrum of that probability function, and you get the line broadening function. Okay. Units of Hertz to minus 1, damping constant, damping constant. Okay. Now, what about those pesky bees? Let me see something. What are you laughing about?
Yeah, I was thinking about Nick Cage.
Yeah.
I was thinking about it then.
I was just worried about those pesky bees. Okay. Here's the deal. I have only been talking so far about spontaneous decay, right? All the A coefficients for this guy to fall down. Well, let me draw this one. I think we were worried about this transition. Was it? Or was it this one? I can't remember. I think it was that one. But in fact, we had to worry about this, 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 in addition to that, and we had to worry about this and that. So this gave us this width, all those. And then that gave us that width. And all we did was worry about the A coefficients, which tells us about the spontaneous K. In other words, the E folding time for this guy to come down, we only talked about the width in terms of spontaneous decays. When we talked about the width of this guy, we only talked about it in terms of its spontaneous decays. But if there's a photon field, the E folding times will be decreased because a photon could come in and induce a transition downward, therefore shortening the E folding time, therefore increasing the width of that energy state. Okay? So it turns out that if you do the math all the way through, that your gamma in is not only just the sum of the A's, but given the intensity coming in, the B's for spontaneous stimulated emission and the B's for absorption. So you have to account, if there's a photon field, for the fact that the E folding time now could be shortened because of induced decays or absorptions, which all that decreases the time that electron would stay in that state. Now, out in the intergalactic medium, photon field's pretty weak. You have to worry about it. So then the question becomes, well, do you have to worry about it in a stellar atmosphere? And now I'm going to show you the answer is pretty much no. Okay? And the argument is right here. Basically, let's take an A star. An A star at 10,000 degrees has a spectral energy distribution that peaks at about 10 to the 15 hertz in the blue part of the visible spectrum. 3,000 angstroms. Now, the intensity, if you go to the black body curve, is around 10 to the minus 4 ergs per second per square centimeter per hertz per radian. What unit is that? We'll get into that in a while. That's just the black body intensity at that frequency if you are an atom sitting in the atmosphere of an A star. Okay? That's the peak of the black body. That's as, at 3,000 angstroms where you see the most intensity. Einstein relations, if you do the math, is that the B for spontaneous decay and absorption are related to the A coefficient by about a factor of 6. Where does that come from? Do you remember I had the 8 pi HC over whatever, A versus B, the Einstein relationships? Do you remember that? No, yes, I wish I knew them by heart. Okay. Remember I said that if you know Einstein A, you can multiply it by these constants and you get the B, right? So if you plug in the H news and whatnot, you get that the B's are about 6 times the A. Not much different. But when now you multiply it by 4 pi and I, which is what you need in the equation, you get that there are about 7 parts per thousand of the A. So they're way down there. Okay. So in other words, if you're an A star, even at the peak of the black body curve, okay, the E folding time is only changed by about a few parts in 1,000. So the width is not changed very much. That's in an A star. Okay. Does that make sense, that argument? Okay. And then I think I even showed that in an O star it's not that important. Okay. I can't remember. Maybe in an O star it becomes more important that I didn't work it out. But certainly, if you need to know the width of a line and you need to calculate it for some reason because it's not in some standard book somewhere, you know that in an A star you can ignore the B coefficients. If you don't know the B coefficients, if the I intensity environment you're in is very intense, way more intense than an A star, maybe even an O star or above, then these terms, 4 pi B I naught, they can start to become on the order of the A's. Therefore, spreading this delta E and changing the shape of that Lorentzian. Okay. That's all I wanted to say about the B's. That, ladies and gentlemen, concludes today's lecture. So let me write down something. Well, let me just show you something. This is the shape of the line coming out of a spectrum. You have a single atom and you fire a flat spectrum at it. Okay? It will absorb light in that pattern. So photons that are exactly at the line center are the most probable to be absorbed. As you get further away from the line center, the probability of them being absorbed goes down. And it's the convolution of these two states that depends upon the e-folding times of spontaneous decay. Okay? What I want you to notice is this is a Gaussian in dotted line. It's the last thing I want to point out. The Lorentzian is a solid line, and the Gaussian of the equivalent width is in the dashed line. Notice that the wings of a Gaussian drop dramatically and go away to zero quickly. But the Lorentzian doesn't. So what we're saying is that the core area of a Lorentzian is very Gaussian-like. But then as you get away from the central region, the Lorentzian has these broad wings. So in fact, as you get further away from the central frequency or wavelength, Lorentzian, let's say you actually still have a discernible probability of absorbing that photon. Okay. And so later on, when we talk about what causes a damped profile in the spectrum, this is going to be the culprit, these broad wings. Okay. Let me just show you the shape of that again. I think I've got a picture of it down here. So for Lyman-Alpha, I showed you this one earlier in the notes. This is the shape. It's a Lorentzian. Now you know it's a Lorentzian. The width here is on the order of 10 to the minus 4 angstroms. And that comes from the e-folding time due to all the physics that I taught you about today. Okay. And so if you had a flat light beam coming in, it would absorb you had a single atom, and you give it a flat spectrum, that single atom would absorb in exactly a Lorentzian shape. Okay? I've given you the shape of the profile, what's called the line broadening function. And I've told you that the Einstein A and the oscillator strength give you the amplitude, but I haven't tied those together yet. And that's what we'll do when we meet next time. I'll tie together, and so you'll get basically not only the shape of this, but you'll get also why it has this amplitude as well. Okay? And so you will now be versed as atomic spectroscopists in understanding why lines have these shapes to them, and why you have damped lines. It's all going to come. Okay. The next stage is, when we get done here, is we're going to introduce the gas physics and then introduce the other things that broaden lines and affect their shapes, and then affect the way that we can pull the physics out of the spectrum to model and understand the physics of the stellar spectrum, or the atmosphere. Okay. Okay.
Video off.